Hi, I'm Samantha Gilbert. I'm a PhD student in astronomy and astrobiology at the University of Washington. So the original title of this talk, as shown on the schedule, was 1D versus 3D models, pros and cons. I actually want to revise the title of this talk because I think that title might be a little too combative. So the new title for this talk is Developing a Hierarchy of Models for Terrestrial Habitability Studies. I'll still offer a comparison of 1D and 3D models, but by the end of this talk, I really want to convince you that both 1D and 3D models have important roles to play in the exoplanet community. So to take a few steps back, let's think about why we model in the first place. So we use models now to predict observables within a practically infinite parameter space as we wait for atmospheric data from terrestrials. Since we're navigating this humongous parameter space, we can grid somewhat coarsely, modeling something on the order of 10 different planets to reveal interesting physical phenomena. But in the future, we'll use our models to interpret spectra and characterize planets via retrieval pipelines. And depending on the resolution of the data we get, there are going to be many solutions that fit the spectra, i.e. degenerate solution families. And all of these solutions need to be vetted with the model. As a result, we may have to run 10,000 cases through the model. For example, here's one square from a colleague's retrieval corner plot. So the retrieved methane distribution here is pretty statistically normal, showing a clear set of preferred values. So he was able to retrieve the mixing ratio of methane in this atmosphere with relative precision. But to get that nice distribution, he had to try mixing ratios of methane ranging from 2 times 10 to the minus 5 to 3 times 10 to the minus 2 moles per mole. That means that for this one single gas, our forward model had to try methane mixing ratios spanning 4 orders of magnitude to arrive at this solution. And that's not even mentioning the distributions for the 4 other gases retrieved in this example. Our retrieval has to try permutations of all these distributions to vet solutions. And even then, some of our gases will be poorly constrained. So to review, we use models to explore phase space to understand key planetary processes and observables, which helps us develop testable hypotheses and support observing proposals. In this modeling mode, we get to turn as many knobs as we want, just like the thousands of knobs on this giant modular synthesizer. Soon, however, we're going to need terrestrial planet models to interpret observations and retrieve planetary characteristics. So in the immediate future, we'll use ground-based ELTs in addition to James Webb to study our best habitable candidates in transmission. Later, we'll hopefully get to use direct imaging to study other habitable candidates around sun-like stars and reflectance. However, spatial resolution mismatches between our models and upcoming data may leave us unprepared for the upcoming observational challenges. So to meet these challenges, we must match the right model or models with the right observations. Our observations may show a diversity of phenomena like composition, rotation, phase dependence, and spatial inhomogeneity, but our observations will also have certain limitations. And we have to think about how we'll apply our models strategically so we can decipher as much as we possibly can about these planets, from the faint halos we'll detect in transmission or the pale blurry dots we'll detect in reflectance. For example, we know that transmission predominantly probes the layers of the atmosphere above the troposphere where radiation dominates and the atmosphere tends to be uniform. As a result, transmission is insensitive to the planetary surface and near-surface atmosphere where hemispherical or other spatial differences are more likely to occur. In fact, the temperature distributions of 1D and 3D models tend to converge in the pressure region transmission probes. Now that we've mentioned 1D and 3D models, let's go ahead and compare them. So the conventional wisdom says that 1D models are relatively computationally inexpensive and can include photochemistry and a more detailed treatment of radiative transport, as well as high spectral resolution. 3D models include atmospheric dynamics and feedbacks with high spatial resolution, and the strengths of each model kind of imply the weaknesses of the other. For example, a major drawback of 1D models is that they cannot currently show where clouds form. Instead, 1D models parameterize over different cloudy and clear sky cases. And this is important because predicting where clouds form impacts the height of spectral absorption features. At the same time, though, we need tight constraints on the atmospheric composition to predict aerosol formation in the first place. And this is where photochemistry in the 1D models comes in handy. So by this point, you've probably heard many talks over the past few days demonstrating the power of 3D models. As a 1D modeler, I of course think we should talk about the strengths of 1D models too. So 1D models can couple climate to photochemistry with rigorous radiative transfer physics, including line-by-line calculations and multi-scattering to predict globally average quantities for a versatile set of planetary environments. Over the next few slides, I'll elaborate on these strengths and what 1D models bring to the table for our observations. So 1D models can include photochemistry driven by the planet's stellar spectrum. For example, 1D models show that for the same atmospheres, Proxima Centauri allows much more methane to build up on the planet than the sun does. As a result, we get very different methane features in transmission spectra for the sun compared to Proxima Centauri. 1D models give self-consistent solutions for atmospheric composition and temperature structure, which allows us to better predict observables in future reflectance spectra. 1D models are also quite versatile. So a good 1D model can model a variety of environments. For example, Meadows et al. 2018 used a 1D climate photochemistry model to simulate highly reducing and highly oxidizing environments on Proxima Centauri b with a variety of compositions and surface conditions and aerosol types. Finally, 1D models can be relatively computationally inexpensive. So this simulated data compares the retrieved spectrum to the true spectrum for James Webb observations of TRAPPIST-1e with a modern Earth atmosphere and no clouds, so it's a clear sky. We can see that even in this optimistic scenario where our spectrum isn't at all truncated by aerosols, the retrieved high-resolution spectra covers a pretty degenerate solution space, particularly as you get to the longer wavelengths. So in this plot, we show that very different atmospheric compositions give spectral solutions that actually all fit the retrieved spectrum with James Webb noise. So computational expense is an important factor in characterizing exoplanet atmospheres because retrieval studies like these are highly computationally expensive. A retrieval study can easily take weeks to run since its forward model has to run through a large, highly degenerate solution space, such as the one depicted here. 1D models have the advantage of being fast enough to accommodate these larger parameter spaces. Now that we know the strengths of 1D models, let's think about upcoming observation methods and how 1D and 3D models can help the community. The first method we'll talk about is transmission, since James Webb will launch relatively soon. The observations we'll get from James Webb provide the most powerful first opportunity to characterize terrestrial planets, but James Webb has a limited number of terrestrial targets. Thus far, our best terrestrial targets are the TRAPPIST-1 system, of course, and a handful of exovenuses. Given recent mass density constraints, we know that these planets are likely to be much more volatile rich than Earth. These environments are going to be strange to us in creation and strange to us in evolution. So to explore these unprecedented environments, we really need 1D models and their versatility and/or 3D Venus GCMs. One of the strongest arguments for using 3D models in this context is that M-dwarf planets are tidally locked and thus may be synchronously rotating, leading to a slow rotation period that could produce large day-night side differences. However, the TRAPPIST-1 planets are so close to their tiny star that even if they are synchronously rotating, they would be rapid rotators. The limit found by Kaparapu et al. Would suggest that B, C, D, E, and F are all rotating rapidly enough to have strong zonal winds and thus likely rapid heat transport. This is an implicit assumption in 1D models, which suggests that 1D models can be applied to these worlds. This suggests that for rapid rotators, the spatial differences relevant to 3D GCMs are less likely to impact global and especially globally observable phenomena. So if 1D is fine for rapid rotators, you might say that that means we definitely need 3D GCMs for slow rotators. So these plots from a 3D GCM model coupled to a chemistry model from Chen et al. Show spatial variations in the distribution of biosignature molecules on a planet rotating with a period of 50 days. So 1D definitely may not be as effective for studying slow rotators, but it's important that whatever spatially inhomogeneous phenomenon you're looking for is actually large enough to be detectable or observable. For example, the molecular spatial variations in these plots may appear large based on just the color gradations, but if you look at the scale, these gradations represent as much as only 25% changes in abundance. For James Webb, we're going to be more concerned with retrieving the right order of magnitude abundance, let alone relatively small changes in abundance. So these past few slides suggest that 1D models offer a lot of advantages for observing in transmission. In the longer term, direct imaging missions like LUPOIR could find and observe the pale blue dots of other habitable zone planets. In particular, a telescope that powerful could use time-dependent and phase-dependent data to create longitudinally averaged maps of a terrestrial planet and would be sensitive to the entire atmospheric column and surface. These maps could help identify distinct surface types on the planet and allow us to search for signs of glint from an ocean as a function of phase. So 3D GCMs can play a pivotal role in predicting the environmental states and potential observables for these spatially resolved, surface-sensitive observations. These future observations would also provide a key data set for interpretation by 3D GCMs. So my main takeaway is that with a hierarchy of models, we can choose the best model or combination of models based on the planetary and observational context we're dealing with. In particular, it is important to center observation technique and data quality when considering a modeling experiment, and the nimbleness of 1D models will likely be extremely important for retrieving planetary characteristics from upcoming observations. Looking forward, it also makes sense to try to bridge the gaps between 1D and 3D models. So I'd really like to encourage you to watch my colleague Andrew Linkowski's talk about his multi-column 1.5D climate photochemistry model. So in conclusion, both 1D and 3D models have important roles to play in the exoplanet community as upcoming missions launch and we finally gain access to terrestrial exoplanet atmospheres. Thank you.